Alright, ladies and gentlemen, so we're continuing 7.2 and talking about areas between curves. Let's talk about what happens, now in a different sense. And so in our last very basic example, we found the area between two curves and we said, hey, it's from this interval, blank to blank, right? And so, and the goal of this video is to understand that when are these intervals really created? How are these intervals created? So the goal is to find the area between curves without given the interval. Alright, and so let's go ahead and try an example, and then we'll kind of summarize how we actually go about getting where these intervals come from. So this is find the area of the region enclosed by y equals 2 minus x squared and the line y equals negative x. And so let's think about this for a second. I need to figure out where uh, our curves are going to actually intersect to figure it out out. So we draw a quick sketch. Draw a quick sketch of what this graph is going to look like here. And so these are not perfect by any means, but I'm gonna try my best to draw it out. And so get a few points out here, get a few points out here. And roughly our graph is going to look something of the nature like this for our parabola. It'll come back through before 2. It'll come back in through there. And then of course the line y equals negative x will go right there to our negative slope. And so the area between the curves we're trying to find, this is the focus point right here, guys. So this is what we're really looking to try to find, is that area right in there. And so let's kind of think about it for a sec, and what makes up these actual interval points that we're trying to find out? Well, hopefully you understand it's the 2 points of intersection, right? It's 2 points of intersection that are created by these two graphs coming together. And so think about back in algebra days. How would you go about finding the quote-unquote solutions to these two equations? Well, hopefully you understood that you can set these two equal together. You could graph as well too. If you're a graphing calc, you do it by that way, find those intersection points, alright? But you can always set them equal to each other, alright? In this case, you're going to get a basic quadratic formula. So setting these two equations equal to one another, we get 2 minus x squared equals negative x. I like keeping my x squared terms positive, so I'm going to go ahead and make this 0 equals x squared minus x minus 2. And so this is a basic factoring problem. You want to factor it out to where you get x, two numbers that multiply to give you the negative but add to give you the positive. And so x plus 2 and x minus 1 in this case. Or I'm sorry, other way around. The end results will be plus 2 and minus 1. I'm skipping ahead on you a little bit. Minus 2 and x plus 1. And then, of course, when you then solve them out, you see your solutions are at x equals 2 and x equals negative 1. So this allows me to now find out kind of what the bounds or the limits of integration are going to be when we actually do find the area of the curve. So remember now for the area, we're trying to go ahead and find out what is the integral of the greater function minus the lesser function. And so in doing so, our area between these two curves are going to be area equals the integral from -1 to 2, in this case, a bigger function minus lesser function, so 2 minus x squared minus a negative x all dx. Alright, well, this is a nice one. I'm just going to take one little simplifier here. So remember, guys, and just because we haven't done this in a while, I'm going to go ahead and separate these out. Remember what this really means. This technically means the integral of each one of these separated functions, right? That's really what this means in the end when we're dealing with, and all these, of course, multiplied by dx. That's really what this represents here. I just kind of wanted to show that again because I feel like sometimes we kind of get lost in what that actually is all relates to. But then, of course, just basic antiderivatives make this to be 2x. Raise the power, divide by the power, so we get a negative x cubed over 3. And then we get plus x squared over 2. And just to keep things a little bit cleaner, remember this is all going from -1 to 2. And so remember, you will substitute all of your 2's in for your x's and then minus the value of all of your x's being -1 in there. And to save a little bit of time, we can do the simple math, and this comes on out to be about 9/2, whatever the units are, being squared. All right. So an interesting little one right there, guys. It kind of goes into a little bit deeper as into where do we actually find some of these uses of integrals when we're dealing with some of these things. All right. All right, guys. Let's give a shot of one on your own before we close up this video here. And let's take a look at y equals, try this one. I want to find the area between y equals 2x squared and y equals x to the 4th minus 2x squared. And you can obviously, you can go ahead and do this, doing the exact same concept here. Now you're going to find this example as number 5 on page 395 in your book, so you can kind of see what the exact intervals are there. But I challenge you, set these two equal to each other, solve for the factors, and see what you can do with that first and foremost. And then you'll go ahead and be able to find out what the upper and the lower bounds are also going to be there. And so, like I said, you can find the graph there on page 5, on page 395 in your book. But you can also double check by setting those two equal to each other and find out what the limits are, and hopefully that you come out to 128 over 15 as your final answer. And on to the next one.